Okay, so the first question we're looking at here is question 2 from page 320. Now, they say that we only have 2 ohm resistors available to us, and we need to make a variety of different resistances up out of them. So the first one we're going to start with is 8 ohms. This is probably the simplest one anyway, because all that we have to do is remember our formula for series resistors, which is the total resistance is the resistance of the first resistor plus the resistance of the second resistor, and so on, third, fourth, fifth. So what we do is just set up 4 of these in series. So 1, 2, 3, 4 resistors. Each of them is denoted by a rectangular shape like this. So if each one is 2 ohms, then one resistor would be 2 ohms, 2 would be 4, 3 would be 6 ohms, and 4 would be 8 ohms. On to part B now. So for part B, they're looking for us to arrange 4 2 ohm resistors in such a way that we get a resistance of 0.5 ohms. So if adding them together in series makes the resistance bigger, adding them together in parallel should make the resistance smaller. So what we can try doing is setting up 4 parallel branches and see how that goes. So our formula for the resistance of a set of parallel resistors is 1 over RT is equal to 1 over R1 plus 1 over R2 and so on. So we've got 4 resistors here, each is the same resistance, so we can sub that in. So 1 over the total resistance is 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2. Simplifying that, we get 1 over RT is equal to 4 halves. We can now cross multiply this out, and we find that 4 RT is going to be equal to 2. So RT is equal to 2 over 4 ohms, or if we put that in decimal form, as we really like to do in physics, 0.5 ohms will be the total resistance for this configuration here. Okay, now we're on to part C, and things get a little bit trickier from here on out. So they're looking for us to get a total resistance of 2 ohms, but using 4 2 ohm resistors to get that total resistance. So what's in my head is I know that if I put a bunch of them in series, it's going to be 8 ohms. If I put a bunch of them in parallel, all of them in parallel, it's going to be 0.5 ohms. So I'm going to have to look for something in between those two resistances. So I'll look for a combination of parallel and series resistors. So let's just see what the resistance would be if we had 2 resistors in parallel, like this. So we could say 1 over R parallel is equal to 1 over R1 plus 1 over R2. We could sub both of them in as a half plus a half. I already at this point know that it's going to look pretty good for me afterwards. So a half plus a half is 1. So 1 over parallel resistance here, it's going to be 1 ohm. So we can cross multiply and we get the parallel resistance is 1 ohm here. So then what I can do, if this whole thing here is 1 ohm of resistance and I need to get to 2 ohms, I can just put another one of these in series with it, and that should work out then. So this is 1 ohm here, and this parallel section has a resistance of 1 ohm. So together it's going to be 1 plus 1 or 2. So we can say RT here is equal to R1 plus R2. Now I know they don't ask you for this in the question, but I'm just including it anyway so you know what I'm at. So then the total resistance here, if we sub in R1 and R2, it's going to be 1 plus 1. So the total resistance is 2 ohms. So for the final part here, they want us to get a total resistance of 5 ohms using 4 2 ohm resistors. So it's going to be bigger than 2, so we're going to have some stuff in series. And handily enough, we know that if we have set up like this with 2 resistors in parallel, the total resistance across this part we've already calculated is going to be 1 ohm. So then we can add on our 2 other resistors, and each one of those is going to be 2 ohms, and both of them are going to be in series. That doesn't look like an omega symbol. Right, here's our next one, and again the resistance for that is 2 ohms. So to find the total resistance across here, you know it's already going to look good. It's going to be total resistance is R1 plus R2 plus R3. We can call that or parallel or something if you want for the parallel section. So that's going to be total resistance is 1 plus 2 plus 2, giving us a total resistance of 5 ohms, which answers our question. Okay, so the second question we're going to look at here then is question 8 from page 326. And you can see I've got an asterisk next to this question on my copy of the book, so you know that it's a tough one. Alright, so they show us a circuit in this diagram that contains a potential divider. So this is our potential divider here. We've got a resistor with then 2 contact points across the resistor. So we can choose anywhere from 0 volts if it connected here, all the way up to 12 volts if it connected on the far side of that resistor. So what reading would we expect to see on the voltmeter? Well, if it was connected here, we said there'd be 0 volts. If it was connected up here, we said there'd be 12 volts. So then you can see it's divided up into 4. So the halfway point would be 6 volts. And then the 1/4 point would be 3 volts here, because it's a quarter of the way between 0 and 12. So part B says, what reading would you expect to see in each of the ammeters? I think this is probably one of the trickier parts. So we can start off with ammeter 1. And let's just look at the current that we'd expect to see flowing through there. So the current flowing through ammeter 1, we can figure that out because we know what the potential difference is across this whole section of current. We can figure out what the total resistance is across this whole section of current. Then we can use Ohm's law if we've got the potential difference and the resistance, and that'll tell us how much current is flowing through this whole thing. And the current that goes through this thing will be the same current as we measure coming out of it. So the current will be the same here, here, or anywhere along here. It will be smaller, say through A2, or through the opposite one here, because whatever amount of charges are flowing through here would have to split up into 2 separate parallel channels. But again, they recombine at the end. So let's start on that. We'll look at the total resistance of this big old chunk here. So let's look at the parallel component first, where we have our 20 ohm and 40 ohm resistors. So the resistance for a parallel circuit, or at least a parallel part of a circuit either, you can say 1 over or parallel is equal to 1 over or 1 plus 1 over or 2. And then substitute that in. So 1 over or parallel is 1 over 20 plus 1 over 40. Simplifying that, we get 1 over or parallel is equal to 3 over 40. We can then cross multiply. So we get 3 times or parallel is equal to 40. And the parallel resistance then is equal to 40 divided by 3, which is 13.33 ohms of resistance. Now, we're not just after the resistance of the parallel parts, we're after the resistance of this whole setup here. So to get the total resistance there, what we're going to do is add our third resistor to this parallel section here, because these two are in series. It's the parallel, and then it follows on with the 20 ohm one in series, or vice versa, depending on which way you read it. So R3 plus the parallel resistance we've already figured out. So that's going to be 20 ohms there for R3 plus 13.33 ohms for the parallel section. So that gives us a total resistance of 33.33 ohms. So again, now that we know the potential difference across this section of the circuit, we know the resistance across this section of the circuit, we can use Ohm's law to tie those two together and give us the current. So Ohm's law is written as V equals I or. V we know is 3 volts. The current is our unknown, we're trying to figure that out. Our resistance is 33.33. So then just to calculate the current, it should be easy enough. It's going to be 3 divided by 33.33. So that gives us a current of 0.09 amps. And I suppose we could maybe make a note here that that's current going through our first ammeter. Okay, so now we're looking at the second ammeter, which is right here next to the 40 ohm resistor. There might be another way of doing this, but to me, what I'd be looking at is the fact that I'm given the resistance right next to this. So if I'm able to figure out the voltage or potential difference across this resistor, then I could use Ohm's law, V equals I or, to figure out the current. So again, I've got the resistance here. I'd have to figure out the potential difference across just this stretch here, which is actually possible. We know the potential difference across this whole thing from here down to here is 3 volts. So if we could figure out the potential difference across the first section here, let's call that V1, then we could take that away from 3 volts. So we'll be left with the potential difference across the second part here. Now this is our hard question, so if you need to pause that and go back over it, please do. Or if you need to ask me later in class, that's grand as well. But let's have a look at it anyway. Hopefully as I do it, it'll make sense. So again, first thing I'm trying to do is figure out the potential difference across just this resistor here. So I'm going to use Ohm's law for that. I know the potential difference is unknown. The current we've already figured out is 0.09 amps that's flowing through that resistor, because it's going to be the same as the current here. And the resistance is 20 ohms. So V, then we're just going to get the product of those two numbers. So that gives us a potential difference of 1.8 volts. Now, like we said before, potential difference here and here should add up to the total potential difference across this part of the circuit. So 1.8 plus the potential difference here should give us 3. So let's get our 3 volts. We'll subtract our 1.8 volts. And that gives us a potential difference of 1.2 volts, which again should be just across this section here. This top one is 1.8, the bottom one is 1.2. Together they give a potential difference of 3 volts. Alright, so now that we have our potential difference across this resistor, we have the resistance of the resistor, we can figure out its current. So again, we're going to go back to all reliable Ohm's law. V equals I or. Let's sub in what we know here. So we know the potential difference is 1.2 volts. And we know that the current is what we're trying to find. And we know the resistance is 40 ohms. So then to find the current, what we're going to do is divide 1.2 by 40. That gives us an answer of 0.03 amps here. And then maybe just as a fun bonus piece of information, if the current flowing through here is 0.03 amps and the current measured up here is 0.09 amps, then we could figure out the current flowing through this branch of the parallel circuit without doing all of the steps we just did there. What we do is we would just realize that if there's 0.03 amps here of current, or 0.03 coulombs per second of charge flowing through, Then the difference between that and 0.09 must be made up in the other branch. So we must have 0.06 amps of current flowing through that other branch of the parallel circuit. So that would give us 0.06 coulombs per second, which is what an amp is. And then those coulombs of charge would recombine at the end, and you get 0.09 coulombs per second of charge flowing through the final part of the circuit there. Obviously they haven't asked us that, but I think it's something they could ask at a higher level. You can figure it out using the method we just did, but you'd save yourself some time. Okay, so then the final part here, part C, wants to know what the value of the potential at point A will be. Now notice that this isn't potential difference, they're looking for point potential at A, which is a pretty unusual thing to ask for. So just as a quick recap here of point potential in a circuit, we generally consider the negative terminal to have zero point potential. That may not actually be the case, we just do it out of convenience. In a circuit it could have a negative potential difference, but yeah, just for the sake of convenience we put this as our reference point. Anything that wasn't applied to a circuit, the actual earth will be our reference point for 0 volts, right? So as long as we have a reference point we can measure potential difference against it. So that means that our point potential, say at the positive terminal, will be 12 volts. If you can't remember which one is going to be positive and which one is going to be 0, just think, potential is the amount of work we'd have to do to move a positive charge to that point. So a positive charge would be quite happy to go to a negative terminal. You wouldn't have to do any work on it. But to move it towards a positive terminal where there's positive charge built up, it would be resisting you every step of the way, so you would actually have to do your work. So for this particular point, we'd be doing 12 joules of work per coulomb of charge, hence the potential difference of 12 volts. So yeah, negative terminal is our point of zero potential. So that means any point away from that, we just measure the potential difference away from 0 volts. So to get to this point A here, we can follow it along. Any point along here, you don't have to do any work from 0 volts. But then to get to this point here, we have a potential difference to go across these resistors. And that potential difference we've already calculated as 1.2 volts. So difference between 1.2 and 0 is just 1.2. Trying to find some empty space to write on this. So our answer for part C is just 1.2 volts. That's our point potential. If it was any other point, for example, if they want to know what the point potential was, here, for example, we could just say 6 volts, or here it's 12 volts, it's just what's the potential difference between there and the negative terminal.